All right, well, it's about that time. Announcements. There is a reflective writing assignment up this week. Don't forget about that. The other thing is, so I've graded a couple of them now, which I had been neglectful of. Last week's reflective writing assignment, I realized I did not change the due date on, and so it's actually due this week. So I've graded the ones that I got as of, I don't know, Monday when I was looking at them. If you haven't done last week's, go ahead and do it. Since the due date was this week, I won't count it late or anything. And honestly, if you've done, all of them, if there's one you haven't done, you're probably going to get 80% or so, even if you do it at the very end. So if you're missing any reflective writings, go ahead and go back and do those now. I will say thank you for sharing your failure stories. Those are always fun to read. I mean, fun in the sense of, seeing what you learned from them and reflecting on that experience. I thought I'd share my own failure story with you. It was my first semester teaching at Geneseo. This is, 15 years ago. It was the fall of 2005. And it was the very first semester that Math Methods had ever been offered. And I was co-teaching it with Pogo. And Pogo was basically developing the class. I was over my head. I was trying to figure out how to teach astronomy for the first time. I was a brand new faculty. And so Pogo was basically doing all the work to put this class together. And I was teaching one section. We had two sections of it back then. Anyway, I don't know if you've never had a Pogo class. They are works of, he's an amazing teacher. And part of what makes him amazing is his amazing preparation. Every single lecture that he ever gives in class is completely typed up, meaning every word that he's going to say, he has planned ahead of time. And he's got a 2 to 3 page, single spaced words, paragraphs, full sentences, everything. And he doesn't end up actually saying those things. And this is just, I guess, part of his prep process for preparing these classes. So anyway, he was preparing these things for a brand new class. He was sending them to me. I was trying to absorb them and teach from them. And it was a disaster. I was horrible. I am exactly the opposite. I need notes. I need bare boned, ideas. And then my brain just goes in real time and I can, his jokes, every single joke he tells is written there, sometimes in italics. So I tried for 2/3 of a semester to teach like Pogo, and it went horribly. I was awful. And I realized about 2/3 of the semester that I just couldn't take his notes and bring them into the classroom. Even if I had gone through them ahead of time and teach, I had to take them from a Pogo looking notes to a my looking notes before, and make it myself. You have to be yourself. So that was a lesson I learned from that. Truly awful. Hard to describe how bad it was. So that was my failure story. There's been lots of other failure stories too, but that's a fun one. Okay. Reflective writing this week. There'll be one last reflective writing next week. There'll be one last homework set that goes up Friday that's due next week. And then midterm 4 Friday next week, and we're done. I will post sometime at the end of this week as I do the equation sheet for that exam. Any questions about logistics or reflective writing or homework or failure? Okay. Then let's get back to where we were. And where we were was thinking about, there it is. I actually want to turn this around today. Let's see if this makes any difference. Probably not, but that's okay. Thinking about doing an example. We've done lots of, you probably are waiting for some examples. Let's do a simple one. And the example is, how fast must you be going to see length contracted by 1%? Okay, so let's invent some observer A in a reference frame of the moving object, right? So something's going to be moving by. Let's invent some observer in that frame. that observed, so we've got some rod, whatever it is, some length of something, L, and it is moving by you at some velocity V. How fast must it be going such that your view of this rod will be 1%, will be contracted by 1%. The observer that is in the frame of the rod will see the proper frame of the rod, right? And so let's invent that observer A. And she will see the proper length L sub A. That's the proper length because that is the reference frame in which the rod itself is moving. What are the length that you're going to see? So you're going to see, you're the primed observer, right? L prime, or just L, let's call it L prime, is equal to the length in the reference frame divided by gamma, right? It has to be shorter. Gamma is always a number that's greater than 1. If you know that the lengths are going to be contracting, you need to divide by this gamma. So basically, what does 1% shorter mean? What is L prime over LA for a 1% length contraction?
Is it 100, 99 over 100?
It's 99 over 100. That's exactly right. 99 over 100 or 0.99, right? So again, we don't know how long LA, it doesn't really matter, but the ratio of L prime to LA must be 0.99, and that's exactly a 1% length contraction, okay? Okay, we also know that L prime over L is just 1 over gamma from this equation. So that must be equal to 1 over gamma. We know that gamma is 1 over the square root of 1 minus beta squared. So this is just the square root of 1 minus beta squared. Beta. So now we can just solve for beta. 1 minus beta squared, take the square of both sides, is sorry, I got messed up here for a second. 1 over gamma. Ah, right. So this must be equal to 0.99 quantity squared, because I've squared both sides and going from this to this. So therefore beta must be equal to, if you just do some algebra, you get square root of 1 minus 0.99 squared. And if you do this out, this comes out to be 0.141. And since beta is V over C, that is V over C. So this, in order to see length contracted by 1%, you have to, that rod has to be going by you at 14% the speed of light, right? So this is, again, even for a very small effect, you wouldn't hardly even notice a 1% change in the length of that thing. You have to be going 14% of the speed of light even to get to that point. So that's really fast. How fast is it? Well, multiply both sides by C, you get like 4.2 times 10 to the 7 meters per second. It's a big, big number. Okay, couple of notes on kappa. Kappa has a couple of units that are very useful for you. For instance, if you get this number and it wants a velocity, you don't have to multiply this by 3 times 10 to the 8 meters per second to plug it into kappa. C is a valid kappa unit. Valid kappa units include C. So you can type in 0.141 C and use C as the units, and kappa will accept that. In fact, that's probably better. It's better to know what the percent of the speed of light is rather than 4.2 times 10 to the 7 meters per second. This is a more useful number even. The other thing that's useful in kappa is light years, CY. Sometimes you'll be asked for distances of things, and we're talking about big distances. And sometimes we'll be dealing in light years anyway. Kappa can handle light years just fine, and the kappa unit for light year is CY. Okay, so that's useful. Now, If you were, so you, let's say we ran the same problem, except that our beta is very, very small. We run into some problems. Here's another example. Length, what is the length contraction on a car moving at 30 meters per second? Obviously, it's going to be a very small number, but how small? This is where we get into problems. Beta is V over C, of course. This is 30 meters per second. That's our velocity, divided by 3 times 10 to the 8 meters per second. This is a very small number. This is 10 to the negative 7. What is 1 minus beta squared in this case? This is 1 minus 10 to the negative 14. Your calculator probably can't do this. If you plug in 1 minus 10 to the negative 14, you're probably gonna, your calculator is probably gonna give you 1. Unless you have a really fancy calculator, in which case you can just do this and not worry about this. But even Excel is gonna have a hard time with this. It's gonna just give you 1 back because this is such a small number, right? And so you need to be able to handle this in a reasonable way. So the trick for these kinds of problems where the speed is much, beta is very, very small, is to use the binomial expansion on gamma. So we know that gamma is 1 minus beta squared to the negative 1/2. If you use the binomial expansion on this, then the first 2 terms are, this is roughly 1 plus 1/2 beta squared for small beta. How small? This actually works pretty well. I mean, pretty well, 1% or so for beta less than 0.2. And if you've got a beta of 10 to the negative 7, it works great. This will give you almost exactly the same answer as this. And it's a heck of a lot easier because often you've gotten some number where you don't even have to do this plus, right? You're taking 1 minus this number or something. And then the ones go away and you're just left with this 1/2 beta squared. And that your calculator can do just fine. You need this particular thing for the airplane problem this week. Okay, let's do another example. A train. And let's say observer on the train is observer A is L equals 40 meters long in its frame. So an observer on train A, observer A on the train observes the length to be 40 meters, and this train is traveling at a very fast train. Beta equals 0.9, 90% the speed of light. We can calculate gamma for this pretty easily, just so we have it. We're going to need it later. 1 over the square root of 1 minus 0.9 squared. This becomes, you just plug it in, you get 2.3. Okay, let's just do some calculations. Calculation 1. What is the length of the train? Definitely, length of train from an observer on the ground watching this train go by. And let's say the ground observer is observer B. So 40 meters is 40 meters. Is A the proper frame or B the proper frame for measuring the length of this train?
It would be the proper frame.
A has to be the proper frame because the train is, observer A is moving with the train, right? So that is the proper frame. So B has to observe this thing shorter, right? So we can say the length of the train as measured by observer B, let's call it length of the train as observed by measure B, by observer B, has to be the length of the train as measured by observer A, which is the proper length, divided by gamma. It's going to be shorter. This is 40 meters divided by 2.3, which is gamma. We already calculated that, and you get 17.4 meters. So observer B on the ground will observe this train only 17.4 meters long, whereas somebody on the train observes the train to be 40 meters long. Okay, that's cool. Let's say now that the train passes through a tunnel. And let's say that that length of the tunnel, and the tunnel is at rest on the ground relative to observer B, is with length 30 meters in the frame of the person on the ground. How long does this tunnel seem on the train? This is observer B to observer A. Now, observer B is at the proper frame for the tunnel, since observer B is at rest relative to the tunnel. So observer B is going to see the proper length for the tunnel, and observer A will see the tunnel contracted, right? So the length that observer A sees for the tunnel will be equal to the length that observer B sees for the tunnel, which is the proper length divided by gamma, and that's 30 meters divided by 2.3, and that's 13 meters. Okay, so this is length contraction like we've seen it before. Observer B sees A's lengths contracted, observer A sees B's lengths contracted. Okay, now, this is where a potential paradox comes in. What if the ground observer arranges to close the doors at the front and end of that tunnel while the train is inside? Okay, observer B, ground observer, closes doors to tunnel while train is inside. Let's just summarize what we've got here. Observer A sees the train, on the train, sees length of the train is 40 meters, length of the tunnel is 13 meters. Observer B sees length of the train is 17.4 meters and length of the tunnel as 30 meters. From the observer B, the train fits inside the tunnel. The train is smaller than the tunnel. From observer A, the train is longer than the tunnel. What happens when B closes the doors while the train is inside? And then let's say opens them again before it reaches the other side. What actually happens? Again, they must agree on what happens. They cannot, if the train hits the forward door or the back door hits the train in one of these scenarios, that has to happen in the other scenario as well. And it seems pretty clear that from observer B's perspective, they can close those doors and then open them while the train is in there and nothing bad happens. It seems like that's not possible for observer A. This is known as the train paradox. Who's right? What actually happens? How do we resolve this paradox? Any thoughts?
Do you have to use the proper measurements? So the train is actually 40 meters long and the tunnel is actually 30 meters long. Is that how you resolve it?
Well, there is no actual, right? Everybody's, I mean, There is a proper length for the train, which is 40 meters. There's a proper length for the tunnel, which is 30 meters. But it's not, it's wrong to say that the B observer's length of that train is wrong, right? That is the actual length that observer B measures for that train. It's not wrong. It just happens to be B's reference frame and B's measurement of that length, right? So it's not wrong. It's just not the proper length.
So would it come down to that B thinks sees themselves as closing the doors at the same time, but A would see the front door close first, and then the front door would open, and they'd pass through the tunnel, and then they'd see the back door close behind them?
This is the problem. They are not going to agree on the simultaneity of those doors opening and closing. What looks like the doors opening and closing simultaneously for observer B cannot be simultaneously closing and opening for observer A. And so if B does that, it's perfectly legitimate. The train is inside there, it fits inside the tunnel. Observer B can open it, can close and open those doors instantaneously. The train is completely inside the tunnel and nothing bad happens. What happens? I'm going to show a short video. You ready for this? I'm going to stop this share. I'm going to start another share. Where am I? Basic. All right, here we go. Okay, so this is kind of cheesy, and I'm playing it at more than faster than speed, one speed, but they're talking really slowly. Anyway, I like this video because it gives you a visualization of some things that are going on that sometimes are hard to picture. This is literally this is way faster than 9% speed of light, because this is way more of a contraction than we just saw. But whatever, it doesn't matter. The faster this train goes, the shorter it's going to seem. I like this video too because it shows all of the X lengths contracted. And this is exactly what's going to happen. The buildings are going to look narrower, the tunnel's going to look smaller, Sarah's going to be squeezed together. Every single spatial dimension in the direction of motion is going to be squeezed down. This is the key. This door has to have opened and closed and opened first. The leading door and the second door has to therefore take place at a different time, or close and open at a different time, sometime later. Okay, that's basically it. There's more to this video. Oops, stop share. There's more to this video, but I'm not going to show it here. If you're interested in going, you can see it. It shows things about how, you know, springs, and it's an interesting video, and some other paradoxes as well. You can take a look at that when you want to. Let's try to visualize this in Minkowski space, though. The video is good, but let's try to put it on a space-time diagram and see if we can make sense of it. So let's go back to whiteboard. So here is a space-time diagram of this event, right? We've got our, let's do it from the observer, from B's perspective on the ground. We've got our x-axis, and we've got our CT axis. We've got our speed of light thing here. And where is, so the world line of the train is 90% the speed of light. And remember, something moving 0 is going to be straight up. Something moving the speed of light is going to be here. You know, half the speed of light, 3/4 the speed of light. The closer you get to the speed of light, the closer you get to the C line. And so the train is going to look like something like this. There's your CT prime space. This is observer A above, and this is observer B. Where is the X prime axis? Remember, the X prime axis is just the same angle away from the C line in the opposite direction. So the X prime axis looks like that. Okay, this is a useful diagram to draw in almost all situations. So let's think about the event that we're talking about, the two events that we're talking about, the opening and closing of the rearward door, and the closing and opening of the leading door, right? And let's say that the trailing door happens at x equals 0, t equals 0, x prime equals 0, t prime equals 0. If this is the trailing door closing, where does the leading door closing and opening happen? Again, from B's perspective, what is true about the time of those two events, the closing and opening of the door?
They would be simultaneous, so so it'd be somewhere along the x-axis.
That's right. They have to share a common time. So somewhere along this x-axis, those two events will happen. And since we called this the trailing edge, let's say that the leading edge happens at some larger x value, might happen over here, right? These are the two events. Observer B, Sarah, whoever it is, sees these two things happen at the same time. Does the primed observer, observer A, see these two things happen at the same time? We already know the answer to that is no. Why not? Well, x prime, just like x is the location of all points at which t equals 0, x prime is the location of all of the points at which t prime is 0. What's true of this point? What's true of the t prime value of that point, of that event? If it's below the x prime axis, what does that mean? If it's below the x axis, that means, what does that mean for time?
It means it would be in negative.
It would be a negative value, right? Any point below the x axis is negative. Any point above the x axis is positive. The same true with the x prime axis. Any point below the x prime axis is negative for the t prime observer, for A observer. Any point above that is positive for the primed observer, right? So this event, even though this event happens at t prime equals 0, this event must happen at t prime less than 0. This, from B's perspective, happened at the same time. From A's perspective, this event happens at negative time, and this event happens at 0. This event must happen before this event. If we were to zoom this, do our stretch squeeze rotation to Lorentz transform this back, the x prime axis would be here. The t prime axis, ct prime axis would be here. We'd have the ct, here's our negative x, here's ct. And this point would stay the same. This point has to move down here somewhere. You're not seeing that. Has to move to somewhere down there as you stretch squeeze this back to this. Make sense? That's the result. The resolution of the train paradox is that even though observer B sees those two things happen at the same time, observer A does not, and therefore it's just fine. Train comes in, this one closes and opens, train continues going. By the time it gets to the other side, this one closes and opens, and both observers agree that the doors don't hit the train, even though both are seeing their relative lengths very differently.
And just to double check, sorry, if you continued that dotted line, the C line,
this one?
Yes. The angle between that and the CT axis would be the same as the angle between that same dotted line and the X axis.
That's right. This angle and this angle have to be the same.
Okay.
And there would be an X axis here, and that would be the same angle also.
Okay, thanks.
Other questions? This is weird stuff. We normally don't think about, the simultaneity is broken. Observers no longer have to agree that things happen at the same time. Not something you probably ever had to think about before. So it takes some time to wrap your brain around this. I'm still not completely comfortable with all of this stuff. It's weird. Okay, let's do one more paradox because they're fun. And this one's an even more famous one, and it's more interesting and more bizarre. So let's do the twin paradox. So the twin paradox goes like this. Twins are born on Earth. Let's call them Bob and Alice, because why not? So they have the same age. They're born, give or plus or minus a few minutes at the same time. Alice, again, the details can vary, but let's just put some numbers in. At age 20, so both of them age for 20 years, and at age 20, Alice boards a rocket and travels at, let's say, 0.8 C to a distant star 4 light years away. And I'll use the kappa CY unit away. She immediately turns around and comes home, which seems like a waste. I know. I would stop and visit that star for a while, but that's what she does. She immediately turns around and comes home. Okay. How old is Bob when she returns? Well, you don't even need special relativity for this problem, right? From Bob's perspective, Alice has boarded a spaceship, gone off in a particular direction for a particular amount of time, a particular distance, and then turned around and come back. All we have to do is figure out how long it took Alice to make that round trip from Bob's perspective, and we've got how old Bob is. So delta T This is just a delta t equals delta x divided by v problem, right? You know how fast Alice is moving and how far she went, then you can figure out how much time elapsed. This is going to be 2 times 4 light years, 2 since she had to go 40 light years away and then come back. So she had to make that trip twice, divided by 0.8c. And the c's actually cancel out here. This is pretty cool. This is the other reason why to do cy, right? Because speed of light cancels out light years, and you don't even have to do any unit conversions here at all. This is just 2. The c's actually cancel out from this, and you get units of years. 4 divided by 0.8 is 5, and so 10 years will have passed from Bob's perspective. So Bob will be 30. How old will Alice be? Well, from Bob's perspective, Bob, remember, sees Alice's clocks moving slowly as she's leaving and moving away and then coming back. So from Bob's perspective, Alice will have had her lengths contract, her time dilated. And so we know that her clocks from Bob's perspective have to be moving slower. And so there will be less time. So again, from Alice's clocks will be moving slower, so a smaller delta t will have taken place. And so we have to divide by gamma. That's that 10 years divided by gamma means multiplying by 1 minus 0.8 by beta squared. And if you 1 minus 0.8 squared is 0.64, 1 minus 0.64 is 0.36. Square root of 0.36 is 0.6. This turns out to be 6 years if you plug in and do the math. So Alice will be 26. So they were twins. When Alice left, they were exactly the same age. Alice took this journey, came back, and Bob is 30 and now Alice is 26. Okay, that's weird, but it's not a paradox. We can, as long as we accept the fact that clocks are going to be moving slower in one frame than another, this is fine. There's no paradox here. The paradox comes when we try to think of this same trip from Alice's perspective, right? What does Alice see? Well, we know that from Alice's perspective, Bob's clock should be moving slower during that whole trip, right? So shouldn't it be that Alice sees Bob younger when she gets back? They don't have to agree on how much time has passed, but they do have to agree on which is older. Who is older when she gets back? So often people think the paradox is just this. How can it be that Alice is younger than Bob? The real paradox is, how can Alice see Bob? How can they agree, right? When both are seeing each other's clocks moving slower during this trip, how can it be that Alice, how can they agree? How can we resolve this problem that it seems like Alice should see Bob being younger when she gets back?
You have to set up which one is the proper frame.
You do, and it does come down to proper frame, and frames are very important for this particular problem. So the solution to this is that Alice has not been in the same inertial reference frame that whole trip, right? If Alice had just continued along, they could disagree about what their ages were. The fact that Alice goes out at one reference frame, right, and then turns around and comes back, well, now she's on a different reference frame, right? There's a one going this way and one going this way. It's the same velocity, but it's pointed in different directions. And it's that turnaround that something weird has to happen. And so let's try to visualize what's actually going on. Okay, so let's draw a Minkowski diagram. I'll make it bigger than this actually. We're gonna need a big one. Okay, so here is, again, we'll draw this from Bob's perspective because Bob hasn't moved. Bob's has been in the same frame the whole time. So here's his X, here's his CT. You can draw the speed of light line. Okay, now where is Alice's world line is gonna look like this on the way out, right? That's CT prime on the way out. Here is X prime on the way out. All right, so far everything looks good. Okay, let's draw some now lines for Alice. This is where things get weird and interesting and fun. What do I mean by a now line? I mean the location of all points that have the same T prime coordinate, right? So if I were to draw now lines for Bob, what would they look like? Well, here is a now line, right? All of this is the now of T equals 0 when Alice leaves Earth, right? All of these points have the same time. All of these points have the same time greater than 0. All of these points have the same time, right? Bob's times are all parallel to the x-axis. Alice's now lines are all parallel to the x prime axis, right? So again, as Alice leaves and is moving at 0.8 the speed of light, that 0 point, t prime equals 0, are all of these lines along this x prime axis. And the next, so you move up from there, right? All of the now lines for Alice are parallel to that x prime axis. So let's draw them back, right? When Alice is at this point in her journey, she looks back and says, aha, that is where Bob is in his timeline at the same time that I'm there, right? I just moved parallel to the x prime axis. Some little time later, I'm here, I move back. But Alice thinks that these 2 points are at exactly the same time, right? And this can continue going. We can draw a bunch of these if we want to. They all, though, have to move back parallel to this x prime axis. Let's draw one more. Right? So you can sort of see it, right? It looks from Alice's perspective like Bob's clocks are moving slow, right? This much time, again, these aren't scaled right, so you can't really do this, but you can kind of see it. From Alice's perspective, it looks like Bob's clocks are running slow. Okay, so what happens when Alice turns around and starts going home? Well, now we have to draw a new set of CT prime and X prime lines. They're not the same anymore. Alice will be on a new world line that will have a new CT prime, we could call it double prime if we want to, which will have a new X double prime set, right? Let's think about what that's gonna look like. Let's say Alice turns around right here. Let's draw one more set of these lines back. Boom. There we go. Okay, now she turns around and moves back towards Earth. I'm gonna need some more room here. She turns around and moves back towards Earth, let's say at this point. Let's say this is 4 light years away. Okay. Let's think about what her world line is going to look like now. You can draw let's draw a new dotted C line from this point, pointing in the other direction, right? So if Alice were to send a light signal back at this point, that's not what these are, by the way. These are the now lines. Let's send a light signal point back. Oh, actually, I've got a better. Let me share my. Hold on. I forgot I had a PowerPoint slide of this. Stop share. Share. Boom. Boom. Look at this. That's fun. Oops. Sure. Here we go. Okay. So here we go. So this is what I've drawn so far in a better, more precise way. And you can see this, right? So again, I've drawn my CT prime axis, I've drawn my x-axis, I've drawn this red line is the light is the speed of light line. And I've drawn these now actually perpendicular to this x prime line. And you can see, again, when Alice gets to this point, she thinks that this is the same point in time for somebody on Earth. Clearly, it seems like these clocks are running much slower. Okay, so this is basically what I've drawn so far. Let's turn around and come back now and see what we've got. So let me stop this share, and I haven't gotten very good at switching back and forth. Bear with me. Okay, now, I'm gonna make this red maybe because it's gonna be confusing with something else. Okay, let's draw the C line, except going in the opposite direction, right? So this is, if at this moment, Alice fired a laser back at Bob towards Earth, it would follow this line. That's the slope equals -1 speed line. Okay, so what is Alice's world line back towards Earth look like from here? Well, she's still moving at 0.8c. She's just moving in the opposite direction, right? So it looks exactly the same as moving in the plus x direction at 0.8c, except it's mirror image. She's moving in the negative x direction. So you can draw the same x CT prime axis, see this direction? That's her actual path back towards Earth. Let's call this CT, I don't know, double prime if you want to. You can draw a new x double prime, right? So this, on the way out, Alice was on this world line. On the way back, Alice is on this world line. And this world line has a very different x-axis than this world line did, right? So think about what's happening now. On the way back, let's say at this point, where is the now line for Alice at that point? Well, the now line for Alice at that point has to follow the new x prime axis, right? So what does it look like? Well, I'm going to follow it perpendicular to that axis, and I'm going to get like that point right there. Another time later, I'm going to follow it perpendicular to the x double prime axis, and the now line is right there. Even right here, just after the turnaround, the now line is right there. So Bob's clocks are still moving slow on the way back. They moved slow on the way out. They moved slow on the way back. Something very interesting happens in the turnaround. It seems like, from Alice's perspectives, that Bob's clocks jump from this point to that point. The now line, Alice's now line, completely changes in the turnaround point. And so, yes, Alice sees less time having elapsed on Bob's clocks while she's moving through space. But in the turnaround point, Bob's clocks seem to jump forward by quite a bit. And that's simply because of the change of inertial reference frame. It's simply because, here, let me share my PowerPoint slide with you. So again, same thing on the way back. We have a new C line. We have a new CT prime axis. We have a new X prime axis. And these now lines, as you draw them back, only elapsed this much on the way out, only elapsed this much on the way back. There was a jump from here to here. Bob's clocks seemed to jump forward. Again, Alice can't observe this directly. She's 4 light years away, right? She can't actually see this physically happen. What does she see? She just infers the time at this location differently when she's leaving as when she's coming back. And when she gets back, lo and behold, when she stops here, she agrees that this much total time has passed for Bob. And she knows she and Bob both agree on how much time has passed for both of them, even though both saw both of their clocks moving slower during the entire trip, except for whatever time it took her to turn around over here. If you take out the clutter, it looks something like this. So this is the jump forward in time that Bob's clocks.
You're not showing your PowerPoint.
Oh, am I not?
No, you're not screen sharing.
That's so sad. Here we go. Okay, let me try it again. I know I'm out of time, but let me just show you this PowerPoint real quick because I'm proud of it. I made this stuff. Okay, here we go. Okay, here's where we were before. Here we are on the way back, right? Same thing, except now the X prime axis and the CT prime axis are moving in the opposite direction because Alice is moving in the opposite direction. And here are these now lines. And you can see time moved slower here, time moved slower here, and yet time, and then we take the uncluttered, time at the turnaround point seems to have jumped from this point to this point. Could you see that time?
Yes.
Okay, all right. I'm out of time. That is the twin paradox. I think this will help for some of the homework problems where you have to think about people aren't moving in this different directions, but light beams are moving around. And the hint I'm going to give you on the homework, 16 is the hardest one on this week's problem set. Draw the picture in 12. You can answer 13, 14, and 15 without drawing the picture, but you really need the picture to answer 16. So if you've got questions about that, obviously you can ask me in office hours tomorrow or send me an email. All right. Thank you very much. We'll pick this back up on Friday.